All right, I put up the redo of Monday's lecture so everybody can see it. So the video's there, and I think it's lecture 34 when I started looking at things. I think I wrote 35 the other day. That's not true. And, can you guys believe today's the 1st of December? All right, Carter's here, Bell's here. No Henry today. Frank's here, Tyler's here, Tim's here, Rose is here. Cool. All right. And then it dawned on me too. Somebody asked me, Nate did. The homework is due today. So I was going to give you guys a take home, remember, hands out today. But I figured I'd better grade the homework first. Make sure you know how to do this. So are there any questions on the homework? 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 Remember homework?
Not really.
Cool. I don't feel so bad either then.
I thought it was almost.
I do feel bad, but it's not that bad. So, final?
Yeah, we just like kind of forget about that too.
No.
Actually, had to add on to that day of misery.
Like we'll show up and you'll be like, oh, I forgot to make it.
Yeah, I watched this video.
That would be good because freaking Ashton put his final on the day of yours. And of the whole week he was on the same day.
Really?
Yeah.
Wait, what? This one's Monday too?
Yeah. It's 8 a.m.
Yeah. What time?
This one's 8 a.m. on
No,
Monday?
no, I didn't say that. I'm saying the whole week you just happen to line up on the same day.
Well, truthfully, mine shouldn't be that hard.
Ask that.
Yeah, that would be another one.
It's going to be 2 exams. I
Do you
think.
remember doing this? Seeing this?
No.
Well, yeah. I love it.
Get a yes back
I
there.
remember the game.
I remember it. Didn't like it.
The candy cane, yes. Actually, it's the thing that's boat davit one. You know what boat davit is? It's how they drop lifeboats over the side of the ships over the ocean. It's the typical, I hate to say it, other than some crazy light pole, the boat davit's the only place I've ever seen this in real life. But I've seen light poles that go up and bend over and they put these great big flare heads on it. It's just an antique looking thing. But now, all right, let's do, oh, this will be fun. The other thing I was going to do for you, and what did I do with it? Here. Okay, so I think what we'll do is I'll work through setting these up for you, and you guys can do them. And then that was simply just a Morse circle problem. This one's the eccentric loading for moments. Okay, so we'll work on those. And these are strictly out of the book. So this was 17.6, 17.9. And then don't ask me why 1717 showed up on this side, but that's the diagram, okay? So, and I also think because I'm seeing the grid lines on it, I shoved this out to you electronically through OneNote, so it's out there someplace, okay? All right, the other thing, as long as I got the overhead on, I went and found you this, and I'll send this out to you as a file later. But this is an old lab that people used to do on beam reactions. And with beam reactions were the shear and bending moment diagrams. Okay? So, who was griping about the final? Who was griping about the final? Here's an easy points. Okay? One of these, how many cases in here? 9. One of these 10 cases will appear on the final. and I'm giving you the cases, okay, and the solutions. And these were all done by students in the past. So like this is Summer Mayer. Don't know who did case 6. Neil did this one. This poor man, Matt, this is the guy. This is the guy. Neil would write with a 0.3mm pencil. And I finally got so pissed off one day, I took a 0.9 out of my pocket and I, give me that 0.3. And I took his 0.3mm pencil with me. Because he print really small. So I gotta get a magnifying glass out to read it. So I got him after a whole semester to finally write big enough that he started using a 0.7. It's like, cool. So I went from 0.3 to 0.9. It's like big, fat, and ugly versus tiny. Yeah, Neil was this guy. But anyway, so I'm going to give you one of these 10 cases. I'm going to send you these files, and you can practice them to your heart's content. Freebie? Pretty much. But the one thing I can tell you so far out of this semester is, shear and bending moment diagrams you guys struggle with. So, make it easy. Do one of these. Okay? Simple, simple, simple.
How many questions do you have on the test?
I don't know. I haven't gotten that far. One so far. So the other part of this is I want to get to the point where I give you combined stress Mohr circle problem, and I was going to give you a take home with a couple problems on it so we can get it done so I don't do it next week. And I was going to do that today, give it to you. Then I realized I didn't grade any of this homework yet. So it's kind of what we're kind of hung up here. So if we do this, I'll get you set up with these problems. And we'll talk about those. And then you can do the Mohr circle calculation. All right. Yeah. Yeah. But I know, it was a week and a half ago. And someplace in between there was get your butt out of the dorms by 5 o'clock, get on a bus or a car and go south, and go home and eat, enjoy yourself, come back to school on time. Some of us did. And then turn it all in today. Which is funny because I did plan on giving you Monday and Tuesday to do them.
I emailed you Friday, so you should have put in an email if I had to do homework. I have a freebie.
So I'm as bad as you guys. So when I took last week off, I literally didn't touch the college until late Saturday afternoon, evening, and some stuff on Sunday night. And I came back on Monday morning and went, okay, I gotta get caught up. So I'm not holding you accountable, but I am gonna make an adjustment here so that A, you can practice these, and then we'll get them out. So I think the other thing is I'll post the solutions when I send these out, the actual answers, not only the work you're gonna do, you know whether you did these right, so that when I give you the test, which I'll give to you on Friday now, and you can do it over the weekend, okay? Make sense? And then the last test, technically what everybody calls the final, to me is just another unit exam, okay? And that'll be on the beam deflection and column bending. That's it. So shear and bending moment diagram, one deflection problem, and one column bending. How many questions? And one of them you ought to be able to pass without any trouble, if you practice this. Make sense? And I will help you if you're having struggles with those, one of those 10 problems, okay? But if you don't do them, I can't help you. Okay, good? Okay. So, yeah, I must have this electronically because I put it in as I printed it from here. So, see if I can find this thing, we'll get it set up. And then we can So it must be under homework. Yes, right there. So, cool. Here's how we're going to do this. I'm going to set this up, and then I'm going to forward this out to everybody so you got it again. Fair enough? All right. Did I hit record? I did. Okay, cool. We're good. Okay, so the first problem right here. A solid steel shaft, 3 inches in diameter, 4 feet long, is fixed at one end and free at the other as shown. The shaft is subjected to an axial tensile load of 5,000 pounds. Compute the magnitude of the force P at the free end necessary to reduce the stress at point B to 0. All right, then compute the maximum combined stress at point A. So what's this actually going to do? Think about it this way. So let's use green. It's going to come off the wall and it's going to go like this. Right? And we want the bottom side here to be 0 pounds per inch squared. Fair enough? All right. And then A is going to be something, right? Because it's going to be in bending. So we're going to put enough P on this. Enough P on this. That sounds really bad, doesn't it? Sounds like something my dog's been doing. We're going to put enough force on this end out here to cause some stress at A, but have 0 stress at B. So there's no compressive stress in the bottom here. Okay? Let's see, what else we want to do to make that easier to set up. Okay, so it's this. So if you take a look at this, your stress in this one, let's do that in black, is this is equal to P over A plus MC over I, okay? Or it could be P over A plus M over S, because it's a solid shape. You could use a section modulus. Okay? So you're going to need those two. Now, what is the okay, so let's do this. Maybe we ought to just do this one outright. Yeah, let's do this one outright, as long as we're having fun here. Remember that image. So first thing we got to do is find A. So I'll give you this one. And that's going to come out as 7.069 inches squared. Okay? And if we use S, it's 2.651 inches cubed. And then we are looking at we need the stress and tension, and that would be 50,000 pounds divided by 7.069 inches squared, and that's going to give you 7,074 pounds inches squared. Everybody with me so far? Because literally we're looking at, ooh, cool, here's something else I'm going to do for you. So in the world of design later on, not in this course, but in design, we're going to worry about that as sigma t and sigma b. Okay, and that'll help you sort out things too. Okay, so we change it from its force to its stress. Okay, so that'll help label those things. So that's my sigma t here. Okay, well actually it's sigma total, but sigma t over here. All right, now for my sigma bending, we're going to be m, c, I'm not using c, I'm going to use s. Okay, but this is plus or minus, okay, because whatever this bending is, it's going to be the same top or bottom, right, if we balance this out. Okay. Oh, why my mask is bothering me today. All right, so in order to get to this, we got to look at 4 feet, 4 feet. Okay, so our I'm going to do this. M is going to be equal to our P times 48 inches. Okay, so we can keep everything in inches here. We could have used 4 feet, but then we got to divide it by 12, so I'm just going to go to 48 inches. Okay, and my S value, which will be 2.651 inches cubed. Okay, and literally I wind up with a plus or minus 18.106 times P. Okay. So far, so good? Okay. So my sigma in this whole bending equation is this. Sigma t plus or minus sigma b. And remember where this came from. This is P over A plus or minus M over S. Okay. The reason to do this in 2 parts, though, is those P's aren't the same. Okay. So if I was doing this for myself and not a problem out of the book, I'd have made this 5,000 F of 4, I guess. Well, actually, don't even have to do that. Just put F. That way we know it's not the P. Make sense? So over here, make that F. Okay? And then this P that's here is still the one causing just my bending. So far, so good? Okay. All right, so in order to do this, we want to do this. We want to set up 7074 pounds per inches squared. The point B is going to be on the compressive side, right? Whoops. So that's going to be minus 18.106 P. And we want it equal to 0 because we want to know that there's no stress out there at B. Make sense? Okay, now it's at Carter. Stress level on the Carter scale 1 to 5.
It should be 0.
Should be 0. Okay.
They all are.
Everybody good so far? This problem's a little neat because it actually works things backwards a bit, but it'll still get you where you're going. All right, so anyways, we can solve for P when we do all this, and P should come out to be 39 or 390.7 pounds. Okay? And that should be in compression. Okay. Actually, it's not in compression because it's not a force, but that's one that's going to cause 0 pounds per inch squared at B. That's because of the compressive side of that. Make sense? All right. Now the point A, so I guess this is point B. Point A is going to be sigma is equal to, I'm going to go F over A just to keep this straight, plus M over S, F over A plus P times 48 inches over the S, okay? Now, this P right here is that value right there, right? Emma? Concept here that's really tricky, right? We have this, yes. But what I'm really interested right here is that you know that P pushing down on the end of that cantilever is only the P that causes the 0 stress at point B, right? Good. Load. Okay. So we plug in the 390.7 pounds, and we're going to get this. So 7.074 pounds per square inch plus 390.7 pounds, and that's 48 inches. No, yeah, because that's my moment. I got to put the moment in there. And the S was, what did I say it was? 2.6. And when I get all done, I should get something like this. Okay? Cool. Fidel, good with this? Still wearing safety gloves. I'll have a rattle on my neck. Now, let's flip this problem the other way for a minute. What if I wanted the maximum stress to be at the bottom and 0 at the top? Okay? So this is for you two. I don't like concrete beams in tension. Why? It's break. And concrete does not work well in tension at all. We'll take some, but we wind up putting reinforced steel in it to do that. What if I wanted that beam to be 0 psi at the top and have all the compressive strength at the bottom? You see how you just flip the equations around? Make sense? That's the reason for doing it with the problem. It's a great way to torque the mechanicals while teaching civils what they need. Oh, wow. I couldn't cover a lot of people. You're lucky I don't have to teach you electrical stuff to do this. It was lost. All right, cool. All right, so back over to this guy. All right, we did a problem like this someplace, didn't we? I would have not given it to you if we hadn't. P is 900. Yep. So this is 900 pounds. Okay. We got an E distance here. They tell us what E was. Yep. E is 600 millimeters. Okay. Which honestly, do yourself a favor. Turn it into meters. That's not 600 pounds. It's 600 Newton or 900 newtons. Okay. And what's this actually going to do? Anybody got an idea? So when we displace this thing, we're going to bend it kind of like this over. Okay? So we're going to have one side of that pipe in compression and one side in tension, right? You see that, Fidel? Tyler? So if I pull 900 down and I'm offset by 0.6 meters, okay, it's going to bend that vertical section over where AB is. Yes? Okay. So in this case, they want to know what the tension is going to be at A and B. So that's tension stress. Okay. Easy enough to do? Emma? Woj? Okay. Well, let's set it up so you guys can solve it. So you need find your areas, find your stress, but your moment will be that force times E. That'll give you your distance, your moment arm. And then your stress is going to be negative P over A plus or minus M. Okay, we're using S. Okay, you could use C or I, but it basically is that. Okay, and all you got to know is one side's in compression, one side's in tension. So, in all fairness, this side's in tension, and that side's in compression.
That's a negative P because it's going downwards, right?
Yep. Normally, it's you could just, but because they didn't tell us P was, I didn't see the negative sign there. Easy enough to do. See, Emma actually remembered. Cool. All right, and the last one is really about Moore's circle. So again, just like we did the other day, find your average, find your R. They didn't ask you to find the angle, did they? Cool. Should be pretty easy to do. There's no Y, there's X and tau. Easy peasy. Cool. All right, and when we're done here, I'm going to send this to you in okay, so that's out in your homework folder. You guys know where that is, right? Anybody not? Pick on Carter. So it shows up right here. Oh, it hasn't got out there yet, but that's the original one. The new one will show up on top of this. And there's the one I wrote on. Cool. All right. We good? Anybody lost, confused, and want to quit? Too late. You're going to suffer through for the next week and a half. The crawl was a week ago Friday. All right. Not that you guys got anything to worry about. You made it this far, you're gonna make it the rest of the way. Okay, so Moore circle, everybody fairly comfortable with now? I mean, I know on the homework, but anybody struggling at all? Then let's move on. We can have some fun. All right, beam deflection. And every year I look at this setup and it's like, this is ridiculous. Let's see, get out of there. Lecture notes and so beam deflection. So there's just a few examples of why we're interested in beam deflection, okay? And you've probably experienced this, but may not know it, okay? But if you stand on a floor, on a wooden floor joist in an old house, you jump up and down, and the floor starts to sway underneath you, that's deflection, okay? There was a great ad when I was a lot younger. Company called True Truss. Their claim to fame was they could put an elephant on the floor and it wouldn't deflect. And it was the stuff with the plywood centers with 2x4 top and bottom, and it was strong, and it was quiet because it didn't squeak, and it could take an elephant. Like, cool, I can make any floor pull up an elephant, you know. Just gotta give me enough material and I can do anything. But their kind of thing was it was lighter, it was easier, and it was a time pushing towards the environmental side of not using so much raw lumber. Because they could literally saw short pieces up and glue them together, and then the center, the first ones came out as plywood, and then they changed them to OSB, and I think they're still OSB now, oriented strand board. Okay, we're basically using chips and other things to make parts and pieces. Okay, but what we're really interested in is how this thing deflects. So think of it this way, and I'm going to use a ruler to make my life just a wee bit easier today. If I have a beam like so, and I bring it up like so, okay. And we box it off, and I have a center line, like so. We got our reactions here, okay? And we put a load right there, okay? This thing, when it's all said and done, should do this, okay? it'll deflect from its center line based on a vertical movement from the center axis or the neutral axis to y. And could be a y of x. And by the way, so this will be 0, and this will be x is equal to some length L. Okay. So far, so good? All right. Now, there's a couple things that play in this, and I'm going to try and simplify this, because every year I do this, I really keep thinking I want to simplify it. We know this happens, okay? So here's some given facts. We have strain, okay, which is epsilon equal to the delta over the delta L, okay? And then we have stress, is that. Can everybody buy that? Remember way back in the beginning, yes? Okay. And then when we get all this said and done, we have remember that? Scary, huh? Realize we've done 13 weeks and we've come right back to the beginning. Never goes away. All right, now if I take these and I rewrite this equation, I'm going to get MC over delta over, that's delta L over the deflection over I, okay? Okay, so there's a whole bunch of trigonometry that goes with this. I guess I got to kind of draw it in order to explain it, but I don't want you getting carried away here. We got some point O. Oh, let me go back up here. Come on. We got some point O here. Okay. This is going to have a radius to here. Okay, so as that bends, it's going to form a curve. Can you buy that bit? Because if I get you to understand that, I don't have to do a whole lot of drawing here. Okay, cool. What's that? I didn't hear you.
Can you say that one more time? Like you said, it bends in a-
Sure. So if it bends, okay, it's going to bend in a curve, right? I'm going to support it out here, and I'm going to bend. I got a point. It's going to have to go in a curve. I don't know what it is. But every curve has an origin that it rotates about. Okay? Everybody else good? Okay. So with that, I have a radius. That's going to be critical to help finding the deflection equations we want to play with. Okay? Because it involves all the trig and all the other fun things, but it gets really obnoxious when I go through all this thing and everybody looks at me at the end going, why'd you do that? So I'm going to skip the malarkey. And if you ever want to see it, I'd be happy to show it to you. But once you get through this, you'll never want to go back anyways. So I'm going to take the R over C, and I'm going to set it equal to delta L over 2 divided by the deflection over 2, which is equal to that over this. Okay? Now when I do this, R then winds up being delta L over sigma times C. Okay? And that little bit right there is going to get us to the point where we can take this group of stuff out of there and put an R value in, okay, the radius. Okay, so we're going to get E is equal to MR over I, and we're going to look at R, whoops, little r, E over I M. M is my moment still, okay? And I guess that's another thing. So now we're using modulus elasticity, not Young's modulus. Modulus of elasticity, okay? Okay, and those are what those are. Okay, let's see, what's the other one here? I got to put, okay, so here's a little note that I'm going to give you. So that R is actually called the radius of curvature. Right? Okay, give me 2 minutes here and we'll get the first part of this set up, and then I'll wrap up the other stuff on Friday. I'll tell you what, we'll wrap that up on Friday. So basically, as I bend that, the sharper the curve, the smaller the radius is. Okay? Think about a circle. You know, I got a 1/2 inch diameter circle, got a pretty tight curve on it, but if it's a 20-foot circle, it's got a big radius. Okay? And sometimes, believe it or not, knowing where the center of radius is important, because you want to know how far it's moving in other places. Then you got to know where that point of origin is. All right, we'll leave it there. All right, you guys do the homework. Get it to me. I'll actually get you the answers so you can have those. And I'll get a test set up to hand out Friday. Okay, and we'll make it due Monday. And these last two chapters here, last two sections are not that horribly difficult. So I guarantee if you get it during class, you will have no problem with it during the exam.
Good day.
You too.